Move on to our second presentation, Relational Network Verification, will be presented by Yifei Yuan. He's a senior engineer in the network research team at Alibaba Cloud. He's leading the research on network verification and validation. Yifei has received his PhD from the University of Pennsylvania. His research interest lies on designing formal techniques and building large-scale systems for validating production-scale networks. Okay, let's welcome Yifei.
Okay, thank you for the introduction. I'm very excited here to share with you a new network verification approach called Relational Network Verification. This is joint work with Xianyang Xu, who's also the leading student of this project, Zachary Kincaid, Arvind Krishnamath, Ratu Mahajan, David Walker, and Nanjai from University of Washington, Alibaba Cloud, and Princeton University. So making changes to a running network is very risky, such as replacing routers or updating configurations. As we can often read on headlines, right, when implemented incorrectly, even very simple network changes may cause severe outages, making businesses unavailable and costing millions of dollars of losses. So according to our internal statistics at Alibaba Cloud, configuration changes alone accounts for 56% of the total network outages, making the #1 root cause for network outages. Oops. So in the last 10 years, we have seen tremendous progress in the research of network verification. Typically, existing approaches can verify for a single network snapshot, can satisfy a spec such as DC1 can reach DC2 as shown here. But unfortunately, applying those single snapshot verification abstractions to validate network changes is really challenging. One of the key reasons is a lack of precise specification. To illustrate, let's consider this simple example. Let's assume the operators want to make a change to the network, such as the traffic on the path ACD, as shown in the blue, will be moved to the path ABD, shown in green. And meanwhile, the traffic of the forwarding path of other traffic should not be impacted, meaning they should stay the same. So let's imagine we want to specify these kinds of intent in single snapshot verification abstraction. Maybe one way to do this is to specify the desired path for each traffic class. However, this is super hard for real-world networks. For instance, to specify the first intent, we have to discover all traffic classes on the path A, C, D, and then we have to specify that each of the traffic class will traverse ABD after the change. It is even harder to specify the second intent. In addition to discover all other traffic classes, we have to discover all their current paths, and then specify that each of the traffic class still follow the discovered path after the change. So this is really hard for real-world networks, as the size of a spec itself is proportional to the entire network size, which is huge. I'll give you some example. For instance, like our global WAN at Alibaba Cloud, we have more than 1,000 routers and millions of traffic classes. So doing this is infeasible. So today, our operators mainly rely on a manual inspection process shown here. So first, they use a simulator called Huoyan to compute the forwarding path for all traffic classes for the network snapshot before the change and after the change. We call them old paths and new paths, respectively. And then they compute the difference between the old paths and new paths, or path diff. And then they manually inspect if there's any incorrect path diffs for any traffic class. So as you can see, that the good part of this approach, the good thing about this approach is that now the operators only need to focus on the difference of forwarding path itself, making it possible to have a manual inspection. But But this process itself is still very time-consuming and error-prone. For a typical change, there may be tens to thousands of differences, but an experienced operator may only inspect tens of differences per day, so making it weeks for even simple changes. Let me show you a real change example of happening in our WAN to further understand this situation. So here we have two ASs, and every circle here represents a group of routers that serves the same role, and circles in the same color represent that they are in the same region. So originally in this network, traffic from DC1 to DC3 follows the path as shown in the blue, and they exit AS1 via B2. So now the operator wants to make a change to this network, that they want to optimize the forwarding path such that the traffic from A1 to D1 will follow a shorter path shown in green, which is A1, A2, A3, and D1. And note that the subpath from DC1 to A1 and also D1 to DC3 should not be changed. And also, at the second intent, the traffic on other forwarding paths should stay the same during the change. So at the first attempt, the network operator updates the import policy for routers in A2 to allow DC3's prefix, and hoping that the traffic would pick A2 as exit point. But however, after inspecting the path diff, they found there's no change at all. So the root cause is that B2's router has a higher preference, so the traffic to DC3 still prefers B2 as an exit point. So to fix this problem, the operator, first of all, hires a local preference on A2 and also lowers a local preference on B2. So after inspecting the path diff, they do observe that the traffic has shifted from region B to region A in AS1 as shown in the blue path. But they also find there's another traffic class from DC2 to DC3 was unexpected changed as shown here. So the root cause is that there's a configuration typo on B2, which causes unexpected change. So they fix this typo, and the forwarding path that was unexpected change before, now changed back. But however, they realize another problem. That is, the traffic after leaving A2 was redirected from A3 to B3 instead of going to D1 directly. Actually, this problem happened after the previous attempt, but due to the information overload, the operator totally missed it. So the root cause of this is that due to the large size of our network, the ISS cost in AS2 is not configured optimally, making the suboptimal forwarding in AS2. So finally, in the first attempt, they fixed the ISS cost, and they found that all path diffs are expected. So in total, this seemingly easy change takes weeks of efforts. So since the network changes are so risky but unavoidable, how can we make it more reliable, efficient, and automated? Our answer to that question is Rela. So the insights of Rela is that, first of all, most of the time and most part of the network stays the same. So can we succinctly capture this part stay the same? And second, networks are large, but the changes are small. So specs talk about changes has a potential to be reasonably small, especially if our language has a good abstraction to collect the changes. Third, stay the same and X changes to Y are relations. So specs should be relations between two networks instead of predicates over one network. So based on those three key insights, we propose Rela, a specification language and verifier for validating network changes. So in Rela, network operator write the change intent in our high-level specification language, And very similar to the manual inspection process, Rela uses this simulator to compute the old path and new path for the network snapshot before the change and after the change. And then the Rela verifier then can automatically verify if the old path and new path satisfy the specification. So let me first introduce the Rela specification language. The high-level idea of this language is to describe the desired relation between the old path and new path instead of the absolute path itself. So an atomic specification in Rela can be specified using the zone modifier pattern, where the zone actually is a path set that we should focus on in this change. And we can specify a zone in reg expressions. And the modifier describes the desired change we want to make to the path in the zone. Some example modifiers are like preserve all paths in the zone, add or remove some paths, replace some paths with others, or even any path in a given range. And the specifications can be composed using concatenation and the prioritize union. So concatenation allows us to describe the desired change for subpath. And the prioritize union basically allows us to describe the if-else relationship. So let's revisit this example and see how we can use Rela to specify the change intent. So recall that there are two parts of the intent. Intent 1 requires the traffic from A1 to D1 to move to the path A1, A2, A3, D1. And second intent requires that the forwarding path of other traffic should stay the same. So first, for the first intent, first step is to specify reg expressions to represent all rotor groups. For instance, if a rotor group A1 has two rotors, A1 and A2, we can write a reg expression like that. And then we can specify the desired change for the subpath using the basic roam modifier pattern as shown on the right. Since the path set we focus on are those starting with A1 and ending with D1, so we can use the reg expression A1 dot star D1 to specify the zone. And for the modifier, since the desired path we want is anyone that goes through A1, A2, A3, D1, we can use any modifier. And then we can specify the desired changes for the full path from DC1 to DC3 using concatenation, as shown on the right. We use DC1 preserve, DC3 preserve to specify that the subpaths from DC1 to A1 and D1 to DC3 should stay the same. And we can reuse the sub-change spec we defined before to specify the desired change for the middle path. And finally, we can concatenate all three sub-specs, which gives us the complete spec for intent 1. So now for intent 2, we want to specify that other traffic should stay the same. So for this kind of spec, we want to specify no change, which can be easily specified using the zone modifier pattern as shown on the right. And finally, we can specify the complete change intent using prioritize union as shown on the right, which gives us a complete specification for this change, which is very compact. Okay, so now let's briefly look into how Rela works inside the verifier. Given the high-level specification language, first of all, it's going to be translated into our intermediate representation, or IR. This IR is designed based on the theory of regular expressions and the regular relations. So those concepts are extensively studied before and is known to have efficient decision procedures. Then we are going to combine the old path, new path with the IR to generate a set of finite state automata and finite state transducers. For check-in, those problems is reduced to an equivalent check-in of finite state automata. Actually, you can read more detail on the paper on how the verifier works. Also, in the paper, you can find more extensions to the language, such as how we can combine header space constraints with Rela specification. Okay, so we have implemented Rela and evaluated based on a real-world dataset. This dataset contains all expert-reviewed high-risk changes in Alibaba Cloud from June 2023 to January 2021. Our results show that Rela is very expressive. Rela can specify 97% of the data plane change intents in this dataset. And also, those specs are very compact. 93% of them can be specified using less than 10 atomic specifications. So here are some examples of the specification in this dataset. You don't need to read all this code, but you can see that writing those specifications for real-world change intents is really easy and compact in Rela. For performance, we evaluated Rela based on our global WAN, which contains more than 1,000 routers, and each router has more than 10,000 prefixes. And in total, there are millions of traffic classes. So you can see that Rela is efficient. 80% of the change intents can be verified within 20 minutes. Just for comparison, the simulation we talked about before uses more than 2 hours to complete. Okay, so to conclude, network changes are risky, and the existing approaches such as single snapshot verification and manual inspection do not suffice. So our key insight here is that the spec for network changes should be relational, meaning a property of 2 networks at once. So based on this insight, we designed Rela, a high-level specification language and verifier for validating network changes. Our evaluation based on real-world datasets show that Rela is both expressive and efficient. Finally, Rela is open source. Please go ahead and check it out here. Thank you.
Hi there, Rob Shakir from Google. Thank you very much. It's an interesting presentation. I was wondering, how well does it scale when you look at like internet prefixes and more complex, like this kind of case where you've got, seems like single exit, seems fine, but like internet prefixes, which might be ECMP'd across different peering points or have multiple exits, etc. How well does the system scale to meet those kind of problem spaces?
Right, so this, I should mention that this tool is verifying on data plane. So as a prefix, this is handled by the simulator called Huoyan. So if you're interested in the scalability of Huoyan, I can say that it can scale to millions of prefixes. So yeah, and for this tool, since it works on data plane, the number of paths is also millions of passes.
But do I have to write a spec that's essentially the entire internet prefix set, or like
no?
Do you have ways to cover that?
No. So yeah. So since the change itself usually is small, right? You don't need to worry about the thing. Most of the changes says that the traffic on one path should be moved to the other path. So you only need to specify the desired change between those 2 paths. Other parts stay the same. You can just write stay the same.
Okay, thanks.
Yeah.
Hi, Alex Krenzel from Berkeley and Google. Thanks for the talk. It's really exciting I fully buy into the benefit of kind of differential way of looking at doing this. One question I was wondering about was, one of the difficulties in getting people to adopt verification tools is asking operators to do any additional work. And here, you're still actually asking them to specify an intent. But I'm curious, I thought a direction you would go in would be extract an intent from a change and then show it to them. And they're willing to look at something. They might not be willing to write something. Why, is that something you can do, and why isn't it something that you did?
Yeah, that's actually is a very interesting direction. Actually, we are pursuing that too. So, but at this stage, we offer other ways for the operator to specify the change intent. What I present here is a core language, right? You can imagine that we provide a web UI for the operator to use the graphics to compose those intents. Or we can provide templates, so the operator only need to give some parameter values to compose this intent.
I cynically still think that asking them to do anything might be too much. But if
Yeah,
you seem to have a structure in which if you have the right language, you could express and extract that intent, which I think would be really cool. But
Yeah, that would be cool. Yeah. Yeah, I agree.
Right. This is Hao Xian from Shanghai Tech University. Yeah, very cool and fun project. So I was wondering the question of this failure resilience property. Is that also part of something that built in the verification that makes sure it has pretty much the same like robustness to like failures, or you have to explicitly say that in this fact?
Okay, so failures, you should be listening to the next talk. But in this talk, we mainly focus on the network changes that we want to make. So yeah, I will refer to the next talk for the failures.
Thank you.